discuss today about Alzheimer's disease neuropathology, which is exacerbated following traumatic brain injury, and neuroprotection by co-administration of nanowired mesenchymal stem cells and trophic factors. So please proceed, Professor Sharma. Thank you for being with us.
Thank you very much for this introduction, and I will present some of experimental data to you. Two important points from previous speakers. One, Professor Ramos portion, that all beautiful hypotheses, they are lost by a defect. This was also the motto of my professor, Prashant Kumar De, who worked with William Feinberg in London, long time, and published papers in Journal of Physiology. The another quote is from Professor Peter Jenner, that it's not the drug, it's the delivery. So these 2 points I will show you here, and of course I am an experimental scientist, not working with clinical aspects. So as you can see that we have some of the experiments on Alzheimer's disease. You know that we cannot replicate any of clinical data in animal model, but we can do, of course, something to understand how it works. And it has a lot of collaboration. Professor Murazani, you very well know. Dr. La Fuente from Spain. Dr. Asia, Dr. Tian from the United States. Dr. Manjulo from Russian Academy of Science. Dr. Patnaik from India. Dr. Mosler is, Dr. Nojari from Harvard University. Dr. Castellani from University of Baltimore. And this is my wife. You can see we have a lot of support, including Department of Defense. So we have to do something that is related with the problems of military across the world, not only the United States. I have nothing to disclose. We remember Professor Stephen Scamper, so he was very influential and a regular participant. So this talk is dedicated to him. Whatever I am saying to you is only my personal interpretation and conclusion. It has nothing to do with any government agencies with whom I am working. In military personnel, they are often very susceptible to traumatic brain injury. And this brain injury, either mild or moderate, lead to different kinds of neurodegenerative diseases. You have heard excellent talk on Parkinson's disease. So Parkinson's disease also, the traumatic brain injury is a risk factor for Parkinson's disease and also for Alzheimer's disease. As you can see, that number of patients from Alzheimer, they are increasing every year, and nowadays more than 5 million people with Alzheimer's disease at different stages, they live in this world. Different national data. The most important point is that, as you can see, that this is normal brain and mild cognitive impairment. We have Amos portion is spot on these things. But in Alzheimer's disease, this is much more bracket here. Another example showing you that this is a normal healthy brain, and this is mild Alzheimer's disease. You can see that ventricles are dilated, some of the hippocampal degeneration is taking place. But here, severe Alzheimer's disease, you can see that the hippocampal degeneration or shrinkage and dilatation of the ventricles are clearly marked. There are many papers on military and Alzheimer's disease and Parkinson's disease, and then when these veterans, they leave the actual combat operation, then most of them are involved with post-traumatic stress disorder. So we have 3 things to understand. One thing is traumatic brain injury, another thing is Alzheimer's disease, and then post-traumatic stress disease. Can we differentiate between these 3? These are some of the data I showed that traumatic brain injury and post-traumatic stress disorder, they are linked via amyloid beta and phosphorylated tau. Well, phosphorylated tau is also linked with Parkinson's disease, but I will concentrate here on some aspects of Alzheimer's disease. This is the publication in 2018, showed that using amyloid fingerprinting, one can differentiate between Alzheimer, healthy, traumatic brain injury, and also post-traumatic stress disorder. How? These are the data. This is from healthy brain, and hardly see this amyloid here. The B is traumatic brain injury, C is Alzheimer, but the most important is that post-traumatic stress disorder, they have the highest level of accumulation of amyloid. The second point is that this is also the healthy control, and this is traumatic brain injury, and again this is post-traumatic stress disorder. You can see that how high the percentage of this amyloid beta. The question is, do we have the position of amyloid peptide all over the brain or certain aspects? Can we differentiate different areas of the brain? And as you know, the brain is not a homologous organ. Each area of the brain is specific for specific functions. For example, hippocampus, memory, impairment, and many other. Thalamus is the connection. So here you can see that using this technique, this is frontal, cingulate is stress brain, parietal, temporal, occipital. Normal, post-traumatic stress disorder, traumatic brain injury, and traumatic brain injury plus post-traumatic stress disorder. There are regional variations in amyloid. So it is very specific. This is a recent paper also published in Proceedings of National Academy of Sciences, one of the prestigious journals in the world, in 2018. And they say that blood plasminogen factor is important. So the point is, peripheral factors may contribute to the pathogenesis of Alzheimer's disease. I can tell you that long ago, Professor Dabson, who is the father of cerebrospinal fluid physiology working in England, and is one of the students, Brasov, is very famous in Alzheimer's disease. For 10 to 15 years, they advocated that Alzheimer's disease comes because the brain cannot expel amyloid beta peptide outside. Okay. So the efflux mechanisms were paralyzed. But we believe since 1982 that probably breakdown of the blood-brain barrier is one of the key factors also in Alzheimer's disease. Now, those people, Brasov and his team, now they are telling that blood-brain barrier breakdown is one of the important aspects in development of Alzheimer's disease. So as you can see, that this is artery and this is venule. You might be knowing that here are the capillaries. This part is from arterial capillary. This is venous capillaries. The blood-brain barrier is lying here and exchange takes place here. Of course, there are some reports that arterioles and venules, they also have some kind of resistance to the blood-brain barrier. And these are the data, I'm not going in details. And then the exchange takes place here in capillaries, and then the blood is cleared by different kind of sciences. This is another example, larger area. So the exchange takes place here. So what happens if this blood-brain barrier is broken down? We have amyloid beta peptide in healthy animals in plant. So why not this is transported into the brain and can be deposited there? This is an example, as you can see with this paper, that amyloid beta peptide can be transported out of the blood-brain barrier. On the other hand, it is also transported in. So both ways are working in Alzheimer's disease. We have to understand different kinds of transporters, different kinds of cellular pathways. This was the result, very old, probably in 1968, but overlooked in Maastricht. They are the first to show in mild Alzheimer cases there was leakage of serum alpin. But this result was overlooked for a long time. We're working in our laboratory Probably we are one of the earliest workers to show that indeed in Alzheimer mouse there is spontaneous leakage of albumin here, and that could be important factor for the pathogenesis of Alzheimer's disease. To prove, we have a drug, we know that symbolizing, and I am grateful to Dr. Moresan who introduced us this. This is a combination of neurotrophic factors, so we can say this is neurotrophic factors and multiple factors. And this was able to prevent this leakage and also some of the aspects of Alzheimer's pathology. So here is the measured amyloid beta, and it is high in Alzheimer. Normal drug given, it is reduced. And when we have given nanoviability, it is significantly important. So here is, the drug is important, but its delivery is also important, as discussed in detail by Professor Peter Jenner earlier. The same thing happened with phosphorylate tau. It was much more decreased, very similar to the normal level when we have used nano delivery. So why nano delivery? I will come later. Then the question comes, our idea is to understand the factors that can exacerbate the pathophysiology of any disease. On the other hand, we have to find some combinations or some drugs they can enhance or induce superior neuroprotection. So these two aspects are our philosophy in our laboratory. So we have used this model of concussive head injury. It is quite common in various aspects, motor vehicle accident, in military personnel, where the skull is not perforated, but this is a weight impact of 0.224 meter. This is called moderate concussive head injury. As you can see here, that we have severe changes in neuronal structure, and the point is that left side, uninjured side, showing much more damage than the injured side. And this is quite common because when this is a counter coup injury, it is always happened that the side that is injured, the brain in a closed cranial compartment bounce to the other side, and therefore the uninjured side get more injury. Some data that we have in our files given by US government, we have more than, this is the data from 12 years, 2000 to 2012, 244,000 almost brain injury cases. In military, this is KeyNote. And you can see that penetrating, severe, moderate, mild, and unclassified injuries. There is also differences between male and female and with the age. So this is quite complicated traumatic head injury. And this cartoon shows that after concussion, the memory, working network, and motor planning severely alters. So we try to create an animal model of Alzheimer's disease because this is very difficult to create a model, and we have used amyloid beta peptide infusion model. This is no way perfect, but it gives some of the results or some of the symptoms that are quite similar to the disease cases. We have advocated earlier that there should be a need for nanotechnology. US FDA is working for human cases, and also the nanotechnological part of the diagnostic is already approved by US FDA, and it is used quite frequently in Karolinska Institute in Stockholm. So the point is that we are studying single therapy, combination therapy, and what are the agents that can enhance superior neuroprotection. Of course, there are some agents, if you combine, the neuroprotection is decreased and adverse effect can come. But I am showing only those things that are doing good. So these are nanowires. They have a US patent of University of Arkansas, and the drugs are labeled or loaded, and this is done in the United States to clear quality control. And many kinds of drugs can be labeled. They can bound with scaffolds when they are injected or administered. The drug is slowly released. And this is Dr. Ryan, and this is Dr. Wang. They have the US patent of these nano aspects of drug delivery. Nowadays, we heard stem cells. Stem cells can do anything, and there is a lot of group on stem cells. There are also genres in stem cells. But nowadays, people are telling that even stem cells can be nanoviral. They live longer, they can have much better effects for therapy. So coming to the point, we have given traumatic head injury, and then we have used these infusion of amyloid beta peptide. Then we have given some drugs and also mesenchymal cells in combination. So what you look, this is blood-brain barrier breakdown because we believe this is important. When there is blood-brain barrier breakdown, the plasma protein enters into the several compartments and it follows by different physical forces. There is an edema there. And the edema is one of the important aspects in pathophysiology of any disease. So this is brain edema. Then we have some pathological index, neural injury, number of cells in a particular area, amyloid beta peptide deposits in those areas, and Alpin cells. You can see saline infusion is clear, nothing. Amyloid beta peptide infusion, you can see that increased blood-brain barrier permeability, edema formation, neural injury, amyloid beta peptide deposits, and number of Alpin cells. They were further aggravated when we combined traumatic brain injury. Then we have used nano delivery of multiple neurotrophic factors, and you can see here that amyloid beta peptide infusion, not only this has significantly reduced these values, but when we have added traumatic brain injury, they were still reduced, but not that very good. Then we tested nano delivery of mesenchymal stem cells, 1 million each time, and you can see that they are able alone to reduce these values, but when traumatic brain injury was combined, the values were not there. So when we have combined both the things together, then you can see that values were considerably reduced. So the point is that if one neuroprotective drug is added with another, maybe they are working at different aspects, but they can induce superior neuroprotection. These are the examples here. You can see that the combination after traumatic brain injury and amyloid beta peptide infusion, we have much better cells than all other conditions. Then people are looking for various kinds of drugs, factors, enzymes. Neprilysin is also one of the enzymes that is reduced in traumatic brain injury and also in Alzheimer's disease. So what does it do in human cases or in physiological properties? The neprilysin shares with amyloid beta peptide, but not with clear fibrillary protein. So we have used combination of neprilysin, as you can see, and here. So the neurotrophic factor infusion together with amyloid beta peptide, and then the same neurotrophic factor with neprilysin. And the important point is that you can see here blood-brain barrier dysfunction. Adding neprilysin has significantly induced much more better neuroprotection than the trophic factors alone. This also occurs in brain edema formation, and also you can see amyloid beta deposit, albumin numbers, and neuronal injuries. So here is another factor. If we combine, then it will induce superior neuroprotection. People are talking about that neprilysin can be used as an infusion to many other kinds of diseases, but they are still under experimental conditions. To find out, since I am a neuropathologist, trained with Inge Olsen in Uppsala University, Sweden, so we look cellular structure as our final parameter, and you can see that this is untreated. We have many more damaged cells here. If we have added neurotrophic factors, there is some protection, but best protection when we have combined these two things together. So the point is, combination therapy is good. We have to find which combination works better for us. But here I caution you that I talked about nano delivery, but nano delivery alone or only nano delivery is not going to induce any neuroprotection. The drugs must be specific. So it's drug and its delivery. Both are important. And here you can see that this compartment is normal compartment, laminectomy and normal. Here is maximum adverse compartment. You can see one drug here, I cannot mention its name because of confidentiality, lies here after a spinal cord injury. But these nanowire drugs under similar conditions and similar dose probably, they are at most adverse condition here. But some of the drugs are in between. So the point is we have to understand which drug is better and which drug is doing good after nanodelivery. How nanodelivery of drugs can induce neuroprotection? The real answer we don't have, but based on literature survey, this paper we have published in Stephen's Capper's journal, we believe that the drugs are penetrating endothelial cells in a very tiny, making tiny hole. They are not enough to induce damage by itself. They release their substance anywhere, either in the basal lamina, glial cells, neurons, or interstitial fluid, and for example, or extracellular fluid, and they can remain there. So this can be analogously, could be mini infusion pump that release that material. They can be there for longer time, and since they are bound to also nanovirus, they are catabolized also slowly. So these are speculations, but probably this is one of the good explanation at the moment. Some of the aspect is discussed in one of the chapters in this Progress in Research book, and I guess the chapter has a copy placed outside for you. And the technological aspect we must understand and should be evaluated neutrally. That was the most important part that Thomas told. So that's why we submitted to innovation. As you can see that this nanowires are collagen and antibodies to even neural nitric oxide synthase and medium granular stem cells, combination in spinal cord injury. This jury gave it top 20% technological award, which means our technology is working. Not so fault because all these are top institutions for analysis. And also Society for Neuroscience organizes nanotechnology and advances in nanomedicine. So we are going on the right track, and I am happy to tell you that also this year too, we have 4 innovations accepted but no award. All innovations cannot get award. But this is one of the examples where we have this specific very hot environment. And this is antibodies to tau and neural nitric oxide synthase in Parkinson's disease. Then there is another drug, DLMDP, using nanowire in concussive head injury. And also we are working, since this is a military sponsored program, neuroprotection in blast injury, and these are recognized as innovation for 2019. We have summarized some of the data in this book you can find outside. This was also given, speaker general was very kind, International Review of Neurobiology is the series editor. So we believe that combination of some good drugs can induce superior neuroprotection. The delivery is given through nanowire technique. We are working different type of nano delivery, and that results maybe we can share with you next year. We believe that nanodrug delivery could be the future, including many diseases that we are trying at the moment to have continuous infusion. This was the book outside. And this book is coming. Thank you, Peter, for allowing us. Probably this will be published at the end of July. We are discussing about brain edema. And we have generous support from various organizations, not taking your time. These are the grant organized agencies, our collaborators, and I am from Uppsala University. Thank you very much for your time.
Thank you very much for your presentation, for sharing with us your extensive studies. If there is any question or comment, please, from Professor Sharma.
So let me ask you, thank you very much. This is a very interesting approach, and I'm sure that there are many more data to support the idea that the blood-brain barrier is an important target when we want to look at neurodegenerative diseases in general and Alzheimer in particular. So you're careful to say that this treatment was helpful against the pathology of Alzheimer's disease. Alzheimer's disease is not a pathological entity. It's a neurological entity, and it involves also cognitive impairment, right?
Yes.
So, do you have any data to share with us to show that the treatment is also helpful in alleviating the cognitive changes in Alzheimer's disease, in this experimental method that you can help also with? Because you know that there is quite a difference between the pathology and the clinical manifestation. And many patients who have many people who have a lot of pathology, old people who have a lot of pathology, do not have any cognitive impairment. So the important thing for us is not to change the pathology. The important thing is to improve the cognition. So we would like to see some effect on the cognition.
Obviously, this is a very valid question, and people are working in the field of a spinal cord injury, and I also worked for a long time, still I'm working. Then there were so many papers that you can improve the sensory motor functions after a spinal cord injury, either in human or in rats. But on the other hand, this pathology worsens. So there is clear delimitation of pathology and sensory motor functions, and also maybe cognitive functions. Some of the sensory motor functions we have evaluated with these kind of treatments, and with the limited parameter or time window we are allowed by our animal experimental methods, we can see that they have some improvement on rotor function, on this walking on, this inclined mesh, and also finding a platform. So some of the cognitive functions or some of the sensory motor functions were improved, but we have some problems of long-term implementation for animal experiments. So I can say that for short period, yes. But if we allow these animals for longer period, as in human cases, I have no idea at the moment. The question is very valid, and we need definitely to have more animal permissions and more investigations.
Thank you very much. Any more questions? If not, thank you very much. And now it's my pleasant task to introduce my co-chairman, Professor Bogdan Lupescu.